All right, we made it. Chapter 2, one chapter in the books. You think about if you had, this is a thought I had as a kid. I guess I was a strange kid, but I used to think, okay, what if you took a rock, something like, this is Mr. Dion's drawing of a rock. Okay, there's a rock on the ground, get some grass or something here. Anyhow, you have a rock, and, I always thought, what would happen if you were to take that rock, and if you cut it in half, and then you took the next piece, and then you cut that in half, and then you took the next piece, and you cut that in half, and cut it 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 in half. Could you how far down could you go and keep cutting something up? And the Greek philosopher Democritus had that same thought. So apparently I wasn't that crazy, but he had it a long time before I did, or a long time before anybody else. He had it way back in the 5th century BC. And what he proposed is that you could take matter and you could cut it and cut it and cut it and break it down until you got to the smallest possible piece of matter that you could obtain, and he called that atomos. And so he didn't do any experiments to prove that, but the atomos idea kind of stuck around for a long time. So again, Democritus, that's the 5th century BC, and it took a long time before an English school teacher named John Dalton came along, and he formulated a precise definition of the indivisible building blocks that we call atoms. And so he came up or postulated this theory in 1808. So this was his hypotheses about the nature of matter. And so Dalton's atomic theory is as follows. So we'll start with the first point, which is he said, elements are composed of extremely small particles that he called atoms. And all atoms of a given element are identical, having the same size. So they all have the same size. They all have the same mass and chemical properties. The atoms of one element, let's say, like gold, are different from all atoms of all the other elements. So say you have another element, say silver. Well, the atoms of gold are different than the atoms of silver. And I know that it's harder for you guys to interrupt me during the lecture when I'm on Microsoft Teams, but I know there's somebody out there who's thinking already, maybe you've taken a chemistry class before, and maybe you're thinking, well, hold on, what about this mass thing? Is that really true? What about, has anybody here ever heard of isotopes? I won't wait for the answer, but I'll assume that maybe one or two people have. And so I didn't say that we completely, that not all of his hypothesis was completely true, but it's pretty darn good. So if we take a look at the next point, number 3, it says compounds are composed of atoms of more than one element. In any compound, the ratio of the numbers of atoms of any two of the elements present is either an integer or a simple fraction. And so even if you've never taken a chemistry class in your life, you're probably aware of things like H2O, and you can see that the elements, hydrogen and oxygen, are present in simple whole number ratios, right? We have 2 hydrogens, that's what this subscript represents, and we only have 1 oxygen. When we have no subscript next to an element, we imply that there's one of those. I'll give you another example. What if you had something like CO2, right? For every 1 carbon atom, we have 2 oxygen atoms. So again, they're present in simple whole number ratios. Let's try another one. I'll give you a really tough one here. I'll really shake things up. C6H12O6, right? Glucose, right? If you've ever studied biology, I know you've seen this molecular formula before, and you can see that the ratio of carbon to hydrogen to oxygen is simple whole number ratio, 6 to 12 to 6. So we don't have any compounds that are like C2.1 to H 86. It's impossible, okay? We don't have any compounds. They must always combine in simple whole number ratios. I'm taking a lot of time here on this slide. Let's take a look at the next one. It says a chemical reaction involves only the separation, combination, or rearrangement of atoms. It does not result in their creation or destruction. And that kind of blew the lid off of alchemy. You've probably heard of alchemists and how they tried to find ways to convert less precious metals, maybe like iron, into precious metals like gold. And there's no way to do that, right? Because a chemical reaction only involves separation, combination, or rearrangement of atoms. We can't create them or destroy them. Now, again, I'm sure there's somebody who's like, is that true, Mr. Dion? What about radioactive elements? What about uranium? That's a radioactive element. Or what about polonium or radon? And that's nuclear chemistry, okay? And we're not talking about nuclear chemistry right now. So let me show you the law of multiple proportions, which is represented on this slide here. You see I have two compounds, and the law of multiple proportions, and the definition is found in your textbook. I'll just tell you what it is. It's that if two elements can combine to form more than one compound, the two elements can combine to form more than one compound, so different compounds, the masses of one element that combined with a fixed mass of the other element are in ratios of small whole numbers. So we see that manifested in this example right here on this slide. You see that we have two elements. We have carbon and oxygen, and we can combine them two ways. We can either make this molecule, which comes out in your car's exhaust, which is called carbon monoxide. You probably have a carbon monoxide detector in your house, and you can see that for every one carbon, we'll assume that, let's make the assumption that this is the carbon and this is the oxygen. We'll assume that for every, we see that for every one carbon, we have one oxygen. So it's a simple whole number ratio. Look, there's another oxide of carbon that's shown here, and it's carbon dioxide. And I know you're familiar with that if you follow the news at all, and you have ever heard of greenhouse gases, of which carbon dioxide is one. You can see that it's a different compound, right? It's a different combination of carbon and oxygen, because for every one carbon we have two oxygens, but they're still present in simple whole number ratios. Okay, so we're always going to see that moving forward. We're not going to see any fractions or decimals or weird decimals of elements combined with other elements in compounds, and that's based on the law of multiple proportions. Let's take look at the law of conservation of mass. There's many ways that you can represent this, and if you look around at all manner of textbooks, they all have different manners of presenting this. But the whole idea behind the law of conservation of mass, and I'll write it down here for you, is that matter cannot be, and I know you know where I'm going, cannot be created, and it can't be destroyed. I should put nor destroyed. So what you put into a reaction is what you should get out of a reaction. So let's take a look at what's going on in this slide here. We have 16 atoms of element X. There is no element X, so it's just a made-up element. We have 8 atoms of element Y. There is an element Y, but I don't think they're referring to that, which is ytterbium. Anyhow, we have 16 of one element and 8 of another. And when we combine them to make a compound, so we make this interesting compound here, and you can see that, again, the law of multiple proportions, that for every Y, right, we have 2 X's, right? And that makes sense because the ratio is 2 to 1. 16 to 8 is the same thing as 2 to 1. Okay, so that works. But let's see. We started out with 16 of X. Do we still have 16 of X? Well, the way that you read this thing here, over here, the way that you read this formula here, 8x2y, is that you can see that each one of these compounds has an X, 2 X's and a Y. So that's represented by x2y. This 8 over here, you basically multiply everything that's in that by the number 8. So what's 2 times 8? That means we have a total of 16 X's, and you multiply Y by 8. 1 by 8 gives you 8 Y's. Well, look at that. It's not magic. Look, 8 Y's, and we have 16 X's. So that's the law of conservation of mass. Now, sometimes a student might think, well, come on, Mr. Deanna, if I burn a piece of wood, I'll sit all night by a campfire, and I'm burning wood, and I'm burning wood, and I'm burning wood, and all I have is, a bed of ashes. That doesn't weigh as much as the wood pile did. Where did the mass go? Well, where did it go? It must have been released in the gases that were evolved when the wood underwent combustion. So technically, if you collected all the ash that was produced and all of the gases that were formed, it should equal the same mass of the wood. So kind of maybe a mind-blown moment, but anyhow, that's the law of conservation of mass. Now, we're really going to switch gears here. Again, there's all kinds of manner of, what am I talking about here? All manner of videos that you can watch on the internet that discuss cathode ray tubes and the history of the cathode ray tube. But I'm just going to kind of go through it quickly here. So a long time ago, back in 1897, a man named J.J. Thomson, among other researchers, measured the mass to charge ratio of an electron, and he won a Nobel Prize for that. And what he did is he took what's called a cathode ray tube, and that's this tube that you see here, which is basically a precursor to the old television set. And maybe some of you are so young that you've never seen a tube TV here, or never seen a tube TV before, but that's what a cathode ray tube is. And basically what they did is they took this glass tube, they evacuated nearly all of the air from it, and then they put two pieces of metal inside that tube to make the cathode ray tube. And you can see that they have one piece of metal here that's called the cathode, and they have another piece of metal here called the anode. And what they do with that cathode and anode is that they hook it up to a high voltage source. And basically, they hook up this high voltage source, and they saw, or what they noticed, is that there was a beam of stuff. And a good scientist should never use the word stuff or thing, but I'm going to get to what it is in a second. They saw a beam of stuff pass from the cathode through a hole in the anode. So they put a hole in the anode, and then it ended up on the end of the cathode ray tube, which was coated with a special substance which caused fluorescence. So it says here a fluorescent screen. Okay, and what they called that ray, they called that a cathode ray. Now it says here that according to electromagnetic theory, a moving charged body behaves like a magnet and can interact with electric and magnetic fields through which it passes. So what Thomson and the researchers he was working with, is they said, let's take that cathode ray and let's subject it to what? Let's subject it to an electric field. And that's what is represented here by this positive and negative. And when they passed it, or subjected it, to an electric field, what they saw is that the cathode ray was deflected down like this. And since you know that opposites attract and like charges repel, he was able to conclude that the cathode rays were negatively charged, right? Kind of interesting. Also, based on the fact that a moving charged body behaves like a magnet, he also subjected it to a magnetic field, okay? A magnetic field, and that's what it is shown right here. Now, I guess he did some of them at the same time so that they would cancel each other out, but what you really need to understand is that he was able to determine that the cathode rays were charged. They must have been charged because they behaved like a magnet. They interacted with a magnet. They were deflected by the magnet as well. They deflected, and as he moved the magnet around, they would deflect in different directions. And also that the particles were negatively charged. So I summarized that right here. It says, because the cathode ray is attracted by the plate bearing the positive charges and repelled by the plate bearing a negative charge, it must consist of negatively charged particles. We know that these negatively charged particles are called electrons. And so that's the name he gave to those particles, electrons. Another thing that I'll point out, and this is something that's just kind of mentioned in our book, and this is beyond the scope of our course, but something else that J.J. Thomson was able to prove is that the mass of an electron, the mass of one electron, okay, was 1,000 times less than a hydrogen atom. Now, again, that's beyond the scope of our course, how he figured that out. But if you think about it, based on Dalton's theory, people thought, well, there's nothing smaller than an atom. So he kind of blew the lid off of that, and everybody was like taken aback, like, whoa, there's something smaller than an atom. So an atom must be made out of particles, that are smaller than an atom. And an electron would be one of those. But if an electron has a negative charge and atoms are neutral, there must be something to balance out that charge. Anyhow, I'm getting ahead of myself, but I just want to point out what else is summarized right here. So it says, he also used his knowledge of electromagnetic theory to determine the ratio of electric charge to the mass of an individual electron. And he came up with this number right here. And this number is really important. You don't have to have it memorized, but it's important to continue on in the story, which we're going to do in a few seconds here when we look at Millikan's experiment. But the number he came up with was negative 1.76 times 10 to the 8 coulombs per gram. Okay, and coulomb is just a unit of electric charge. So keep again, you don't have to memorize that number. It's just a good idea to know that J.J. Thomson discovered the electron using a cathode ray tube. But I want you to keep this number in your back pocket right now, because we're going to move on and we're going to talk about the charge of an actual electron, right? Because this is the charge for a gram of electrons. Now, what about the charge of an actual electron? And that was determined by Millikan. And Robert Millikan did a really interesting experiment here. And I'm probably already taking up too much time on this, but it's kind of interesting. So what he did is he set up this really interesting apparatus that I have shown here, where he took oil and he used what's called an atomizer. And you're like, well, it kind of looks like an old-timey perfume spray bottle to me, Mr. Dion. That's basically what it is, okay? And he was able to take some oil droplets, and he sprayed them into this, the droplets made a fine mist, and then he put them, or sprayed the fine mist into this apparatus that's shown here. I can't think of a better word for it right now, but what would happen is you can see that he had some plates here. So he has some electrically charged plates, and some of those oil droplets would fall through a hole. And this is the little tiny hole. I know it's really hard to see it, but some of those would fall through that hole. So these are the drops. And again, maybe you have the textbook open and can see it better than me, but there's little tiny drops there. So those are oil droplets. Now what he did is he took an X-ray source, okay, and he bombarded the air inside this chamber right here, the lower chamber. He bombarded it with X-rays. And what that did is that caused electrons to be liberated from the atoms or molecules that make up the air. And those electrons stuck to the oil droplets. So now, so if you're like, what the heck, Mr. Dion? Okay, so all he has at this point, all he has is an oil droplet that is covered in electrons, okay? And that has some kind of charge. Now, if you think about the electron, I'm going to draw it right here, and you guys know that electrons are negatively charged, so I'll put a negative charge. So what he was able to do is, you see how the electrons, or sorry, the oil droplets coated in electrons were falling down, right? You guys know what gravity is. You know that because of the weight of the electron, the weight, okay, is equal to the mass multiplied by the gravitational force. But here's the cool part. Are you ready? Okay, strap your skates on, Gordy. Here's where it gets really interesting. What he was able to do is he was able to take these electrical plates, and it's not shown here, but he was able to take a dial, okay? This is Mr. Dion's dial, and he was able to crank that dial up, right, to increase the positive charge here. And so he was able to use the electrical force, or electrical force, I'll just write electric force, okay, which is equal to the charge of the electron times the applied magnetic field, Q times E. Okay, so he was able to balance that out. And are you ready for this? He was able to make the oil droplet hover in space. Okay, and so he knew the gravitational force. Okay, he knew the charge per gram. Okay, and he knew the applied magnetic field. And from that, he was able to determine the mass of an electron. Okay, so he was able to determine that, and it's not written out here explicitly for you. I can do that. So we have the charge of an electron, and we have the charge to mass ratio. Basically, you just multiply those two together, and you end up with the mass of an electron. So that's what Millikan did. He was able to determine the mass of an electron. Now, again, I'm not going to ask you, oh, please write me a 20-page essay on Millikan's experiment. No, I just want you to have an idea where it comes from. So what you need to know is that Millikan, he's responsible for determining the mass of an electron. And probably, let's just shift gears for a second. You're probably like that's kind of a heavy subject, Mr. Dion. Well, look at that. 9.1 times 10 to the, are you ready? Negative 28. You know, is it just me, Jerry, or is that a small mass? That's a small mass, right? That's a really small mass. Okay? And you're like, well, duh, I get it. That's small. Well, it is. It's extremely small. And that's going to be very important as we move forward, because it doesn't account for the mass of atoms. And so I've been doing a lot of gear switching here, but, you know, we're still kind of at the beginning of the course. And before we move on and discuss how the nucleus was discovered, we have to switch gears and talk about what's called radioactivity. Now, radiation is the emission or transmission of energy in the form of particles or waves through space or a material And there's different types of radiation. We can have electromagnetic radiation, like radio waves, infrared, gamma rays, so on and so forth. And we can have particle radiation. And so the three types of, it shouldn't say here, the three types of rays are produced by the decay or breakdown of a radioactive substance such as uranium. Now, this is kind of a heavy subject covered in one slide. So if you're like, Mr. Dion, are we going to talk about nuclear chemistry? Yes, we will talk about nuclear chemistry, but that's quite a ways away. That's probably not until November, December. So I just want to bring home some really crucial points to wrap up our discussion of the discovery of the electron and the nucleus and the neutron and the proton. And that's that alpha rays consist of a positively charged particle called an alpha particle, okay? And therefore are deflected by a positively charged plate. So we have some kind of radioactive substance here, okay? And then we pass it through an electric current. We have a negative charge and a positive charge, and you can see that the alpha particles are going up, right? They're attracted to the negative charge, so the alpha particles are positively charged. So what you need to know is that an alpha particle is positively charged. A beta particle, you don't even really have to worry about that tonight, but I'll tell you that a beta particle is negatively charged, and you can see how the beta is attracted to the positive electrode. And then the third type of radioactive radiation consists of high energy rays called gamma rays. Gamma rays have no charge and are not affected by an externally applied electric field, and you can see that manifested here. So let's get back to brass tacks here and talk about the alpha particle, okay? So an alpha particle, if you've ever studied chemistry before, I can tell you that an alpha particle is really nothing more than a helium nucleus. So it's just 2 protons and 2 electrons. So where we are at this moment in history, okay, is that scientists knew there was something smaller than an atom. It was called an electron. Okay, so they knew what an electron was. They knew how much an electron weighed. They knew the charge of an electron, but they didn't know what balanced out that charge, right? They knew that atoms were neutral. Okay, atoms are neutral, but there's got to be something to balance out that charge. And so what Thomson proposed, this is called the Plum pudding model. So the Plum pudding model, you can Google it if you want, the Plum pudding model. Plum pudding, I mean, Thomson was British. We don't eat a whole lot of plum pudding over here in the States. So I've heard people call this the blueberry muffin model. So basically, the model is that all the electrons are just kind of interdispersed throughout the positively charged like sphere, okay? Now we know that that's not true, okay? We have a more sophisticated model of the atom now, but how did we get to that, okay? Well, this is probably one of my favorite experiments in chemistry is Rutherfords Experiment. So Rutherford was a chemist from New Zealand, and he won the Nobel Prize, not the Nobel Prize. He didn't get an order of Nobel Prize. He got the Nobel Prize for this experiment. Are you ready for this? Who's ready? I just need to know that my students are out there. I'm lecturing to the wall, so. Anybody out there with me? Excuse me. All right, great. That's awesome. That's awesome. Glad you guys are still with me. I know it's not the funnest thing to do to sit in front of a computer, but I commend you. Somebody says, let's go. Let's do it. Okay. Well, let me show you. This is one of my favorite experiments. I like to nerd out on this experiment. So what Rutherford did is this. Now, he wasn't alone. He had other scientists with him, but I guess Rutherford gets all the glory. He took an alpha particle emitter. Now, I told you that an alpha particle is it's basically nothing more than the nucleus of a helium atom. But anyhow, the nucleus hadn't been discovered yet. So he took these alpha particles, okay, and he took a piece of gold foil. Now, I'm sure that you've all seen a piece of gold foil, but gold is very malleable. It can be hammered into really thin sheets. And so the piece of gold foil, okay, so here's my piece of gold foil, right? I can't afford a piece of gold foil. Are you kidding me? But here's your piece of gold foil. If you were to take your eyeball and look right on the edge of the gold foil, okay, just look at the edge right here. That's the edge, okay? This is the edge of the gold foil. So you can see that it's only 2 atoms deep. It's very thin. Now what he did is he fired these little tiny particles, these alpha particles at the gold foil. And what he figured is that based off of, let me back up, based off of this model, the Plum pudding model, he's like, I should just be able to shoot my alpha particles. Whee! I should just shoot them through, and they'll just fly through because, the electrons are just, interdispersed throughout the positively charged sphere of the atom. And what he found is that he said, and you probably read the textbook, I'm sure you all did, what he said in the textbook is the famous quote is, you ready for this? He said it's like firing a 15-inch cannonball at a piece of toilet paper, and it bounces back at you. He said that's what happened. They had no inclination that this was going to happen. So you see how most of the alpha particles, right? These are the alpha particles. Most of them just went through. Wee, wee. But you look very carefully and look at this one here. Ay, ay, ay. Look at this guy. It ricocheted. It came right back at them. Okay? And so that was how they discovered that atoms, so the atom has a positive charge and it's concentrated in the center, and we call that the nucleus. Okay? And they were able to determine that the proton has the opposite charge of an electron. Now, the mass of a proton is almost 2,000. It's 1,840 times heavier than the mass of an electron. So now we've got the charge of a proton. We know that the proton is in the center of the atom based off of this experiment, and we know the mass. So we get the mass and the charge of an electron. We get the mass and the charge of a proton. We know the proton's in the middle of the nucleus. Okay, giddy up. We got that. Now, before we move on and talk about the neutron, I just want to tell you about the size of the nucleus compared to the size of an atom. Okay, so it says here the atomic radius, the average atomic radius, okay, the average size of an atom is 100 picometers. So pico is 10 times, pico is 10 picometers is 10 to the negative 12 meters, right? So 100 picometers. Now the nuclear radius is 5 times 10 to the negative 3 picometers. And if you're like, well, what's the difference? Okay, here's the description that they use in our book, and it's pretty powerful. Okay, if you had the Houston Astrodome, which one of my students told me, they're like, Mr. Dion, that's been torn down. Okay, if you had, where do the Broncos play? Is that Coors Field, or is it, I forget, is it Dick's Sporting Goods Arena? I don't know. Wherever the Broncos play, okay, in that giant field in Denver, if you were to take a pea, like a pea from a pea pod, and put it in the middle, that's how big the nucleus is compared to the size of the atom. Okay, so a nucleus is very small compared to the size of an atom. All right, so Chadwick came along, and he won the Nobel Prize for discovering the neutron. But here's how they discovered the neutron. I'll go over this quickly because I want to get into something else. But I'm already spending too much time on this historical stuff, but it's kind of fascinating. Okay, he said, okay, you have a hydrogen atom. The hydrogen atom has 1 proton, and a helium atom has 2 protons. Now, the mass of a proton is constant, so they said, well, a helium atom should weigh twice as much as a proton. And you notice here that they're just leaving out the electron because it weighs so much less than a proton, so you can basically negate the mass of an electron. Don't have to think about it. But what scientists discovered is that a helium atom weighs 4 times as much. Like that, it weighs 4 times as much as a hydrogen. So they said, well, damn, there's got to be another particle. And so Chadwick discovered the neutron by bombarding beryllium foil with alpha particles. And what he found is that it gave off a new particle. Now, there's a lot of, I could really ramble on about this, and I probably wouldn't be the best guy to teach you everything about the physics behind this, but basically he discovered a new particle that was emitted, and that is the neutron. Okay, the neutron. And the neutron has almost the exact same mass as a proton, and it has no charge. That's why they call it the neutron, is because it's neutral. Now let's summarize a hell of a lot of blah, blah, blah on this beautiful table here, table 2.1 from your textbook. You can see again that the mass of a proton and a neutron are virtually identical. There's a very small difference, and that the mass of a proton or a neutron is it's like pretty close to 2,000 times, right, that of an electron. An electron is a lot lighter. You can do that math on your calculator. The charge of a proton, The charge of a proton or an electron are opposite. Okay, they're the same charge, but they're opposite. And we assign it a unit charge of -1 or +1. And of course, a neutron has no charge. Is it 6:07 already? Have we been in class since 5 o'clock? Have we been in class since 5 o'clock? Mr. Dion gets a little forgetful sometimes, you guys. Brittany says yes. Okay, is anybody into having a break? Having a short break? Okay. Okay, I got 2 people who vote. Oh, I got more people. Okay. Who vote a break. So I'm going to stop recording just for a second here. Over here. And stop recording.